Welcome, everyone. I'm excited to kick off today's presentation on understanding probability. This is the first slide, so I just want to briefly introduce what we'll be exploring. We'll look at what probability really means, why it's important, and how it can be applied in different situations. So, let's get started and dive into the fascinating world of probability. Let's take a closer look at slide 2, which outlines the key components of our discussion on probability. First, we have the definition of probability. This is the foundation of everything, understanding what probability truly means and how we quantify uncertainty. Next, we move to terminology used in definition, which is crucial because the language we use, terms like experiment, outcome, event, helps us precisely describe and analyze probabilistic scenarios. Then we have illustrations, which are practical examples that bring these concepts to life, making them easier to grasp. Finally, we come to theorems of probability, the fundamental rules and formulas that govern how probabilities combine and relate to each other. These components are interconnected. They build upon each other to give us a comprehensive understanding of probability as a mathematical and real-world tool. As we progress through the presentation, keep in mind how each part fits into the bigger picture of analyzing and understanding uncertainty in various contexts. Let's start by understanding what probability actually means. Probability is essentially a way to measure the likelihood or chance that a particular event will occur. It's a fundamental concept that helps us quantify uncertainty in a mathematical way. When we talk about probability, we're assigning a number between 0 and 1 to an event, where 0 means the event cannot happen, and 1 means it is certain to happen. This concept is crucial because it allows us to analyze and predict outcomes in various fields, from finance to science. Throughout this presentation, we'll see how probability helps us make informed decisions by understanding and managing uncertainty. Let's take a closer look at what this slide is telling us. Here, n represents the number of unfavorable events, while m stands for the number of favorable events. Now, when we're calculating the probability of an event, we use this simple ratio, p, a equals m divided by the sum of m and n. In other words, if we know how many favorable outcomes there are and how many unfavorable ones, we can determine the likelihood of the event happening by dividing the favorable outcomes by the total number of possible outcomes. This concept becomes even clearer when we consider an experiment with a specific number of outcomes. Say, n outcomes that are all equally likely and cover all possibilities, meaning they are exhaustive and mutually exclusive. If m of those outcomes favor event A, then the probability of occurring is simply the ratio of m to the total number of outcomes, which is m plus n. Understanding this helps us grasp the fundamental idea of probability. It's essentially a measure of how likely an event is to occur based on the possible outcomes. And of course, this ties into the overall theme of understanding uncertainty and making predictions in various scenarios. Let's take a closer look at the terminology used in the definition. Understanding these key terms is crucial because they form the foundation of the overall concept we're exploring. When we say definition, we're essentially describing what something is, but to do that effectively, we need to be clear on the specific language and terms involved. For example, terms like system, process, or stakeholder each carry specific meanings that influence how we interpret the entire definition. Recognizing these helps us avoid misunderstandings and ensures we're all on the same page. Throughout this presentation, I want you to keep in mind that mastering this terminology not only clarifies the individual concepts, but also enhances our ability to connect these ideas to the bigger picture. So, as we move forward, pay attention to how these terms relate to the overall theme of effective communication and understanding within the context we're discussing. So, on this slide, we're talking about what's known as a random experiment. Essentially, it's an occurrence that can happen multiple times under almost the same conditions each time. But here's the interesting part. Even if the conditions are similar, the outcome can't be predicted with certainty beforehand. That's what makes it a random experiment. It's a fundamental concept because it helps us understand situations where we can't be sure what will happen, but we can still analyze the probabilities. This idea is a cornerstone in the overall theme of probability and statistics, as it sets the stage for how we model and interpret uncertain events. Let's take a closer look at the concept of sample space and sample points. Imagine we're rolling a die. The possible outcomes are the numbers 1 through 6. So, the sample space, which we denote as S, includes all these outcomes. S equals 1, 2, 3, 4, 5, 6. This set represents every possible result of our experiment. Each individual outcome, like rolling a 3 or a 5, is called a sample point. The sample space can be finite, like in this case, since it has a limited number of outcomes, or it can be infinite if there are infinitely many possible outcomes, such as measuring the exact time it takes for a car to travel a distance. Understanding the sample space helps us organize and analyze the possible outcomes of any experiment, which is fundamental when we're exploring probabilities. It connects directly to our overall theme of understanding how to predict and quantify uncertainty in various scenarios. So let's talk about what an event actually is. Essentially, any subset of the sample space is called an event. Now, if we think about the sample space itself, which contains all possible outcomes, it's obvious that both the null set, which we write as O stroke, and the entire sample space S are considered events. For example, suppose we have a specific event like E equals 2, 4, 6. If we know that the number of elements in event A, which we denote as N, A is 3, that tells us there are 3 outcomes in that event. Recognizing these basic building blocks, events as subsets of the sample space, is fundamental because it helps us understand how probabilities are assigned and how different outcomes relate to each other within a larger context. Let's look at the concept of exhaustive outcomes. When we toss a coin, there are only 2 possible outcomes. Either it comes up heads or tails. These are what we call exhaustive outcomes because they cover all possible results of that experiment. Now moving on to an example with a die. When we throw a die, there are 6 possible outcomes. The numbers 1, 2, 3, 4, 5, and 6. These outcomes are also exhaustive because no matter how we roll the die, one of these 6 results must occur. So by exhaustive, we mean that we've considered all the possible outcomes of an experiment. And importantly, one of these outcomes will definitely happen each time we perform the experiment. This idea is crucial because it helps us understand and predict the chances of different events in probability. In summary, exhaustive outcomes are all the possible results that can happen in an experiment, ensuring nothing is left out. Outcomes are said to be mutually exclusive if the happening of one outcome completely rules out the possibility of any other outcomes occurring at the same time. For example, think about tossing a coin. If the coin lands on heads, then it's impossible for it to land on tails in that same toss. That's what we mean by mutually exclusive outcomes. They cannot happen together. This concept is important because it helps us understand the different possible results in a chance experiment and how they relate to each other. Recognizing mutually exclusive outcomes allows us to better analyze probabilities and make more accurate predictions. It's a key idea that ties into the overall theme of understanding how outcomes behave in probability. Outcomes are said to be equally likely when none of them is expected to happen more often than the others. In other words, each possible result has the same chance of occurring. This concept is important because it helps us understand situations where there's no bias or preference toward any particular outcome. When outcomes are equally likely, it simplifies the process of calculating probabilities because we can assume each one has an equal shot. This idea ties into the broader theme of probability, where understanding the likelihood of different events allows us to make informed predictions and decisions. So, recognizing when outcomes are equally likely is a fundamental step in analyzing many probability problems. When we talk about 2 events being independent, what we mean is that the chance of one happening doesn't change no matter what the other one does. In other words, if event A occurs or doesn't occur, it doesn't influence the likelihood of event B happening. It's like flipping a coin and rolling a die. These 2 actions don't affect each other. Now, on the flip side, If the occurrence of one event does impact the probability of the other, then we say these events are dependent. For example, if you draw a card from a deck and don't replace it, the chances of drawing a certain card on the next turn change because the total number of cards has decreased. This distinction between independent and dependent events is really important because it helps us understand how events interact with each other in probability. It ties back to our overall theme of understanding uncertainty and how different factors can influence outcomes. Recognizing whether events are independent or dependent allows us to make more accurate predictions and better decisions based on the situation. Now, let's take a closer look at the illustrations on this slide. These visuals are designed to complement and clarify the key points we've been discussing. When I mention illustrations, I mean the diagrams, charts, and images that help bring the concepts to life. They serve as visual aids to make complex ideas more understandable and engaging. As you can see, each illustration highlights a specific aspect of the topic, emphasizing the most important concepts we want to remember. Connecting these visuals to the overall theme of the presentation helps reinforce our message and ensures that the information resonates. Remember, effective illustrations are not just pretty pictures, they're tools to enhance comprehension and retention. So, as we go through these, keep in mind how they tie into the bigger picture we're building together. Let's take a closer look at this slide. We're focusing on the probability of certain outcomes when rolling an unbiased die. Specifically, we're interested in two cases. First, getting either a 5 or a 6, and second, getting a 6. So, imagine rolling a fair die. It has 6 equally likely faces. The question here is, what are the chances of these specific events happening? For the first part, we're looking at the probability of rolling a 5 or a 6. Since these are 2 outcomes out of 6 possible, we can see that the probability is the sum of the individual probabilities. Now, for the second part, we're interested in just rolling a 6. That's a single outcome, so its probability is simply 1 out of 6. Understanding these probabilities helps us grasp the fundamental concept of equally likely outcomes, which is key in probability theory. It also sets the stage for more complex calculations and real-world applications where chance plays a role. Remember, when we talk about these probabilities, we're considering every face of the die as equally likely, which is what makes the calculations straightforward and reliable. Let's look at the first part here. When we talk about getting either a 5 or a 6, we see that n(e), the number of favorable outcomes, is 2. Since the total number of possible outcomes, n(s), is 6, the probability p(e) is simply 2 divided by 6, which simplifies to 1/3. Now, moving on to the second part. If we're only interested in the chance of getting a 6, then n(e) is just 1 because there's only one 6 on the die. Again, since n(s) is 6, the probability p(e) becomes 1 divided by 6, or 1/6. And just to clarify, when we throw a die once, there are 6 possible outcomes, numbers 1, 2, 3, 4, 5, and 6. That's why n(s) equals 6. So the key takeaway here is understanding how to count the favorable outcomes and total outcomes, then dividing to find the probability. This approach helps us solve different probability questions systematically. All right, let's look at this example involving 2 dice thrown simultaneously. The question is, what is the probability that the total sum of the 2 dice equals 6? Now, to approach this, I want to emphasize the importance of understanding all the possible outcomes. When you throw 2 dice, each die has 6 faces, so the total number of outcomes is 6 times 6, which gives us 36. This is our sample space. Next, we need to identify all the specific outcomes where the sum of the 2 dice is exactly 6. For example, if the first die shows a 1, the second must show a 5. If the first shows a 2, the second must show a 4, and so on. It's key to list all these pairs, and there are exactly 5 such combinations: 15, 24, 33, 42, and 51. So the probability of getting a total of 6 is the number of favorable outcomes, which is 5, divided by the total number of possible outcomes, 36. This illustrates how probability is about understanding the ratio of favorable cases to total cases, especially in scenarios with equally likely outcomes like dice throws. By grasping this, we can see how to approach similar probability questions systematically. Let's take a closer look at this example. Here, our event E consists of the specific outcomes where the sum of the two dice is 6. These outcomes are 15, 24, 33, 42, and 51. So if you count them, there are 5 such outcomes, meaning NE equals 5. Now, since we're dealing with the probability of this event, we need to consider the total number of possible outcomes when 2 dice are thrown simultaneously. Each die has 6 faces, so the total number of outcomes, NS, is 6 times 6, which gives us 36. Therefore, the probability of event E happening, where the sum is 6, is the number of favorable outcomes divided by the total possible outcomes. So P, E equals N, E divided by N, S, which is 5 divided by 36. This example nicely illustrates how we calculate probabilities based on counting favorable outcomes relative to the total possible outcomes in a random experiment, reinforcing the fundamental idea behind probability theory. Let's take a look at the concept of playing cards. Playing cards are a great example of how simple tools can be used for a wide variety of purposes. They're not just for games. They also serve as a useful metaphor for understanding different strategies and decision-making processes. Each card in a deck has unique value, and that value can change depending on the context, just like in real-world scenarios. This highlights the importance of flexibility and situational awareness. When we think about the overall theme of this presentation, playing cards remind us that sometimes success depends on knowing which card to play and when to play it. They emphasize the importance of strategy, adaptability, and understanding the rules of the game, whether in business or other areas of life. All right, let's take a closer look at the colors of the cards. When we talk about suits, we often associate them with specific colors. For instance, the club and spade suits are traditionally black, while the heart and diamond suits are red. This color coding isn't just for aesthetics. It plays a significant role in how the game is played and how we interpret the cards. In this slide, you'll notice the different suits and their corresponding numbers, like the heart with a 4 or the diamond with a 3. These numbers help us understand the hierarchy and value within each suit. The number 2 next to the heart, for example, indicates its rank within that suit, just like the 4 next to the club. The key takeaway here is that the suits and their colors are fundamental to card games. They help differentiate the cards, organize strategies, and sometimes even influence the rules of the game. Recognizing these color associations and suit rankings connects directly to our overall theme of understanding card design and how it impacts gameplay. Let's take a moment to talk about the theorems of probability. These theorems are fundamental because they give us a solid mathematical foundation for understanding how probabilities behave. They help us determine the likelihood of complex events based on simpler ones. For example, the addition and multiplication theorems are essential tools that allow us to analyze combined or sequential events effectively. Recognizing these theorems connects to our overall theme of building a structured approach to probability, making it easier to analyze real-world situations with confidence. So, mastering these theorems is key to applying probability theory accurately and efficiently. Now let's look at what happens when events are not mutually exclusive. In this case, if 2 events A and B are not mutually exclusive, it means they can happen at the same time. So when we want to find the probability that either A or B occurs, we can't just add their individual probabilities together, because that would count the overlap twice. Instead, we take the sum of P A and P B, and then subtract the probability that both A and B happen, which is P A B. This way, we're avoiding double counting. The formula for this is P A B equals P A plus P B minus P A B. Contrast this with the case where events are mutually exclusive, meaning they cannot happen together. In that scenario, the probability of either A or B happening is simply the sum of their individual probabilities, because there's no overlap to worry about. That formula is P A B equals P A plus P B. This addition rule, often called the OR theorem, is fundamental because it helps us accurately calculate combined probabilities when events can overlap. Remember, the key point here is understanding whether events are mutually exclusive or not, as it directly impacts how we apply these formulas. Connecting this to our overall theme, mastering these concepts allows us to better analyze complex probability scenarios in real-world situations. Let's talk about the probability of event occurring, but with a twist, when we already know that event B has happened. This is what we call conditional probability, and it's denoted as P/B. Essentially, it tells us how likely A is, given that we know B has occurred. Now, an important point to remember is that if A and B are independent events, meaning the occurrence of one doesn't affect the other, then the probability of a given B is just the same as the probability of A on its own. In other words, P/B equals P/A. This concept is fundamental because it helps us understand how information about one event influences the likelihood of another, which ties right into the overall theme of understanding probabilities in different contexts. Let's take a closer look at the case of independent events. When two events, A and B, are independent, the probability of both happening at the same time, which we write as PAB, is simply the product of their individual probabilities. In other words, PAB equals PA times PB. Now, there's also a more general way to express this, which involves conditional probability. If PB is not 0, then the probability of both A and B occurring can also be written as PB multiplied by the probability of a given B. Similarly, if PA is not 0, PAB can be expressed as PA times the probability of B given A. What this all means is that the probability of two events happening together can be found by multiplying the probability of one event by the conditional probability of the other, depending on which event has already occurred or is given. This concept is known as the multiplication theorem, and it's fundamental in understanding how probabilities combine when events are dependent or independent. It helps us see the connection between joint probability and conditional probability, which is key to many applications in probability and statistics.